Welcome to the afternoon session. I am.
Right away.
All right, so first up, we have Petros Drineas, who will talk about randomized linear algebra for interior point methods.
Thank you very much, Rachel. So I should say that the talk is going to actually be more about interior point methods and essentially how they perform when you are allowed approximate solutions to the system of linear equations that underlies interior point methods, as opposed to randomized linear algebra, which is my favorite topic. But on the other hand, the tools we're going to use in this talk from randomized linear algebra are going to be fairly straightforward and actually known for a while. So we're going to black box some things. We're going to make them plain nice for interior point methods, but really most of the work has been on understanding interior point methods under noisy updates, basically. So I should start by saying, acknowledging the collaborators. So this is joint work. It's a few papers, actually. Joint work over the past 2-3 years with Chaim Avram from the University of Tel Aviv. Agniva was my PhD student. He did most of this work during his postdoc at ORNL. Gregory Dexter is still my PhD student, and Palma London from Caltech at the time, she's now at UCSD, was visiting us, talking to us about this line. So this is a crowd that I don't really need to talk about motivation, why we care about continuous optimization. I will say that compared to all the difficult problems I've seen over the past couple of days here about non-convex optimization and whatnot, I'm looking at the simplest possible case. I'm looking at linear programming, very convex, very well behaved. For me, I should say this started, I was trying to do L1 regression on genomic data, and the genomic data I had access to was really large. Like, think of a matrix with 500,000 rows, 2 to 3 million columns, dense matrix. So I wanted to do L1 regression there, and it's a linear program, but it didn't scale well, of course. So I wanted sketching-based, faster algorithms for this particular setting. Turned out that this was not kind of the right thing to do because there were better models, what is called a linear mixed model, LMM, for this particular data. So we followed a different approach, but at the same time, it got us thinking about linear programming and what we can do with linear programming and interior point methods. So on one hand, of course, continuous optimization is important in pretty much all of machine learning, but also because you relax many combinatorial optimization problems to linear programs. Matrix sketching, you know, we've been working on this for almost a quarter of a century now, and we understand how you can essentially create a sketch of a matrix that consists maybe of a few rows, a few columns, a few elements, or multiply a matrix by a random Gaussian matrix or something like that and create the sketch. And we understand that this works well in many settings. Also, the topic here was, of course, to sort of combine the two. Now, interior point methods, as we will discuss, are iterative algorithms, so you need to see how the error propagates over iterations. And that's pretty much what we're going to do. The standard setting, I know you've been through tutorials here in the bootcamp week. I actually watched those tutorials. They were really nice, both for things like linear programming as well as for matrix sketching, but I will repeat some of the material to make sure we're all on the same page. Standard form for LP, primal dual. You are looking at a minimization problem subject to AX equal B, X being non-negative. This is your primal variable. I want to think of this as A being an M by N matrix. So my primal variable is n-dimensional. The dual problem, of course, B transpose Y, a maximization problem now, subject to the dual constraint, which includes the dual variable Y. This is an m-dimensional variable, and the slack variable S, which is n-dimensional. Now, Y is not constrained, but S is. S has to be non-negative as well. And we know that because of strong duality, we get that the primal optimal C transpose X and B transpose Y at optimality, of course, they match. And kind of a picture here, of course, a simple polytope. I have 6 constraints, 2 dimensions, and the optimal solution always at the vertex. But the methods we are going to be exploring, interior point methods, they don't look at vertices. Don't worry much about the applications. It appears everywhere. Here's our objective. My objective was to look at kind of textbook approaches. So I wanted to look at very practical algorithms. As I said in the beginning, my focus was genomic data, but it could be applied elsewhere. I wanted to look at interior point methods because they are the technique of choice in practice. Now, interior point methods, if you know a little bit about the history for linear programming, they came, of course, after simplex. They came after the ellipsoid. Interior point methods, in the beginning, there were the long step, the short step ones, and then you got predictor corrector, which are very good both in theory and in practice. They achieve the same running time guarantees as short step methods, but they also have the practical efficiency, if you will, of long step methods. I wanted to analyze kind of the predictor corrector, the standard IPMs, the ones that are in some sense used in practice as well. And I wanted to use iterative linear solvers, things like preconditioned conjugate gradients, instead of more exotic tools like fast matrix multiplication, because this is something that in practice probably would not work so well. I also wanted to have efficient preconditioner constructions. That's where the randomized linear algebra is going to come into play, instead of mechanisms like inverse maintenance, which again, how practical they are, remains, I think, to be seen. And we wanted to be able to extend the classical theoretical convergence guarantees for interior point methods for linear programs when we use inexact linear system solves. Okay. And there was work, of course, in this area before, and I think we're able to get some newer bounds here as well. Just as a reminder, the optimality conditions, we're going to look at the primal problem and the dual problem at the same time, so we're going to solve them both. X primal variable, Y the dual variable, S is the slack. And remember that XYS is a primal dual optimal solution if it is basically primal feasible. This is primal feasibility. Dual feasible, this is dual feasibility. They need to be non-negative. And the last condition is the complementary slackness, which I don't particularly like this notation, but what it basically says is that either Xi, the primal, or Si, the slack, they have to be zero at optimality. So one of the two has to be zero. At least one of the two has to be zero. Now, for those of you who work in randomized linear algebra, you're going to recognize why I'm doing this. We're going to focus on problems where the constraint matrix A is either tall and thin, so you have a lot more constraints than variables, or short and fat, so you have a lot fewer, so you have a small number of constraints, a lot of variables, or it has exact low rank. So for general square matrices, I cannot do much, and this is because I cannot design good preconditioners for those matrices using the tools that I have at my disposal. A special case would be Laplacian matrices, symmetric, diagonally dominant, more general, but I'm not going to get to that at all. So tall and thin, short and fat, exact low rank at this point. You could add a little bit of noise and that would work, but we're not going to worry about this. Standard methods, of course, simplex is probably the first thing that comes to mind. Fast in practice, exponential time worst case complexity. Interior point methods, ellipsoid I'm skipping. Interior point methods, they are the fastest. They're fast in theory, weak polynomial time convergence. They are often faster in practice than large-scale LPs. As I was working in this area, I talked to people at Gurobi and other places, and they told me that in many cases, they will run an interior point method to get close to the optimal solution, but then they would switch to simplex to actually get the actual optimal solution. So combination of the methods also exist. I like this picture just because it gives you an idea of how interior point methods operate for linear programming, and kind of the important thing is that you go through basically the middle of the polytope, or certainly the center of the polytope. You follow approximately what is called the central path here until you get close to basically an optimal solution, which will lie in a vertex potentially. You get epsilon close. This is the epsilon neighborhood of the solution. We'll give some definitions in a minute. And this is, in some sense, what interior point methods do. Now we'll look at another picture to show what predictor corrector methods do. That's kind of the textbook presentation. And what you look at the duality measure. So you look at the distance between the primal optimum and the dual optimum. This is the primal, the mean. This is the dual, the max. And when it gets to zero, you know that you've reached, of course, optimality. It's exactly equal to X transpose S. This is just a one-line thing. And in primal dual IPMs, the idea is to follow this central path here. Now, the central path satisfies Xi Si equal to mu for some parameter mu. This is the centrality parameter, but this is not easy. Of course, you are not going to be able to satisfy that in every iteration, so you are going to just be close to that. And I'm using here an L2 norm definition of the neighborhood. There are other definitions as well, where you're trying to get Xi Si minus mu, sum the squares of those differences, the two norm basically, to be smaller than some theta times mu. And that's the neighborhood. How do you compute updates? So interior point methods, they're iterative methods. You have a current iterate, you move to the next iterate. To find the next iterate, you compute the so-called Newton direction, and it solves this system of linear equations. Now you can break this up. I do want to highlight one thing. If you look at the first line, this line here that has A and zeros, and then delta X, delta Y, delta S, these are the primal update, the dual update, the slack update. You're going to see that A times delta X, the other two, of course, cancel out, has to be equal to 0. This is telling you that delta X, the update on the X direction, has to be in the null space of A. And that's to ensure feasibility, basically. And this is fundamental in the proofs of IPMs for interior point methods for linear programming. You can sort of play with these equations a bit, and you can get this system of equations. This is nice. This first equation is the so-called normal equations. Here's what you get. You get A d square A transpose. D square depends on the current iterate values, x size and size, and the size. Basically, D is just x to the half, s to the minus half, where x contains it's a diagonal matrix that contains the xi, s is a diagonal matrix that contains the si, the slack. This is symmetric positive definite, so you like this, of course. On the other hand, this could be quite ill-conditioned, especially as you approach convergence. This is the system you need to solve if you follow the normal equation path. You need to solve this system to get delta y. Then delta s and delta x are what we call mathvex. They are easy to compute. There is no system to solve here. You just do some matrix vector multiplications, and that's it. So all the work is basically here. We're going to focus on this. I'm going to present an alternative approach, the augmented path approach, in a bit as well. Predictor corrector. So if you want to think about predictor corrector algorithms, they're iterative algorithms. They take two steps. They solve two systems of linear equations at each step. There is a predictor step and a corrector step. The predictor step, what it does, it takes you a little bit further away from the center, so it doesn't really follow. It doesn't lie in a good enough neighborhood, perhaps. But on the other hand, it makes good progress towards the objective. And then in the corrector step, you get back to the close neighborhood to get good performance. So it combines the good things from long step methods that make good progress, with short step methods that, at least theoretically, converge faster. So predictor corrector takes these two steps in the analysis. Here's where we're going to focus. So we want to solve this system, A d square A transpose delta y equal to some right-hand side P. And the question is, how do we solve it? If you solve it with direct solvers, that's the standard analysis. What if you throw in like an iterative solver and get back an approximate solution? So what happens? You lose feasibility, you lose various things, and the question is, can you still prove something? And this question has been around for a while. Now, the result I'm going to describe, I don't think I've seen it as such in the literature. This is for predictor corrector methods. It says the following, that as long as you satisfy these two constraints, if you're familiar with numerical linear algebra, this is a forward and a backward error constraint. So the first constraint is saying get an approximate solution, delta y tilde, so that delta y tilde minus the exact solution with respect to the energy norm is at most delta. So this is basically saying that your approximate solution minus the exact solution is small, is good enough. And then you have a residual constraint as well, which is saying that if you hit your original matrix by the approximate solution minus the right-hand side, if you solved it exactly, that would be 0. It's not going to be 0. It has to be less than or equal to delta. As long as these two things are satisfied, this is with respect to the energy norm, this is just the 2 norm, you are going to be able to get the guarantees of the standard predictor corrector algorithm as long as delta is sufficiently small. So you get the iteration complexity of the standard predictor corrector, which is order root n is the number of variables, times log 1 over epsilon, where epsilon is the neighborhood size that you want to converge to. Notice the logarithmic convergence, of course, which is what you want to get. And approximate solutions can be tolerated as long as the error is less than epsilon, the neighborhood, divided by the square root of n. This sounds small, but iterative methods can get this kind of convergence guarantees pretty much in time that is logarithmic in this error here. However, the final solution will be not be exactly feasible. It will be epsilon feasible. You lose feasibility, and you need to be a little bit careful in the analysis to make sure that this loss of feasibility does not propagate in a bad way. So this was kind of the first result we got. I think, I suspect that some variant of this result should be known to numerical analysts because In practice, that's what everybody does. They don't solve the system exactly. They use some iterative method to solve it. Here's the next thing that we try to do. Is there a way to actually approximately solve the system and still somehow get a final solution that is exactly feasible? Is it possible to correct for that error? So that got us thinking along the lines of, can we somehow take this approximate solution delta y tilde and fix it so that the system, so that the next iterate is exactly feasible, and can we analyze this? So this is the result that we got. We introduced a new vector v. This is going to be n-dimensional again. This is going to be under your control. So you control v. You're going to get an approximate solution delta y tilde. You get to control v, and delta y tilde has to satisfy now this new equality. And there are various ways to state this equality, but for now, let me state it as is. It has A, it has S inverse, which is the diagonal matrix of the slack variables, times v. You compute delta x tilde just like before, you don't change anything, and you fix delta x tilde by putting a little bit of a correction here. This guarantees now that delta x tilde is lying in the null space of A. You control v, you come up with some approximate solution delta y tilde, but they have to be connected in this way. And I like this a lot, because when I saw this, I realized that, now you can go back to the standard analysis. It doesn't exactly work, but it almost works. And you could go back to the original analysis and guarantee, of course, feasibility at the end and make your life a little bit simpler. And then we found a very similar idea in a fairly old paper, actually, as I was giving this talk in front of the optimizing crowd, in front of the optimizers. They pointed me to this paper by Monteiro and O'Neill, which had a very similar idea, but could not construct V in a good way, in an efficient way. Here's the structural result. The structural result is same. Get an inexact solution delta y tilde, anything you want. Get a vector v, again, anything you want. This is going to be under your control. The only constraint is that this equality has to be satisfied, and the 2 norm of v has to be order epsilon. Epsilon is the target accuracy. Then you are not going to lose anything in terms of convergence. You lose a constant here, actually, but that's all you lose. So predictor corrector is going to converge in the same number of iterations, basically, with the approximate solution, as long as you do this correction. Final solution is exactly feasible. You don't lose feasibility either. And it's up to you how to construct V. So you control that. I'll give a construction of V. That's where randomized numerical linear algebra will come in. It's not the most elegant one. I don't think it's the most elegant construction, but it's a construction that is faster, that is fast enough for our purposes. This is a structural result, by the way. There is nothing randomized here. This is just a structural result. I was giving this talk a couple of months ago in front of a gang of optimizers, and Jacek Gondzio pointed me to this paper of his where they are not solving the normal equations. They are looking at the so-called augmented system, which is this system here. It's equivalent to the previous one, but they solve this system for delta y tilde and delta x tilde at the same time. It's worth noting that when they do approximate solvers for this system here, they still want to emphasize that A delta x tilde is equal to 0. So they force delta x tilde to lie in the null space of A. We tolerate noise there and we correct it, unlike what was done in previous work for the augmented system. But the claim is that for certain instances, using specialized Krylov solvers and some special preconditioners, they're actually able to make this happen in practice. So I just wanted to put up that reference as well for an alternative way to think about this problem. How can we solve the linear system while satisfying the previous conditions? And I'm going to be wrapping up in a few minutes. Precondition conjugate gradient, again, off-the-shelf approaches. The preconditioner, for those of you who are doing randomized linear algebra, what we are doing, if we think of a short and fat matrix, A times D will be M by N much larger than M. You sketch it. So you compute ADW, and you use that, you run an SVD, or you could do a QR as well, and you use that as your preconditioner, basically. Forget about the math. This has been done actually for over a decade at this point in randomized linear algebra. It's very similar to BlenderPick, what Chaim Avron has done, very similar to LSRN, what Michael Mahoney has done. So we sort of know how to do this properly. And then you iteratively solve it. You use, we had to prove a couple of results for preconditioned conjugate gradient, but nothing particularly new as far as I can tell, at least. As long as your preconditioning is good enough, it converges exponentially fast to the right solution, so you get the bounds that you want to get. I'll skip that. Let me talk about this. So essentially, all we need to do is to run a precondition conjugate gradient method for log n over epsilon iterations. This is the inner iteration, so you have the outer iteration of the IPM, that's root 10 log 1 over epsilon, forget about the mu. The inner iteration runs for another log n over epsilon for the precondition conjugate gradient, but the preconditioner has to be good enough. No dependency on any kind of condition numbers for the AD matrix. You get rid of all that because your preconditioner is good. The correction vector, so you have to construct the correction vector. The construction is this ugly thing here. This is reverse engineered. This worked for us. That's how we basically did it. But one has to say that this is free. All the running time that you need to spend is done in the construction of the preconditioner. Once you have your preconditioner, this is literally 2 or 3 mathvecs. So it comes for free because of the construction of the preconditioner. I'm pretty sure there are alternative ways to construct this vector V. We haven't looked at that. Running time complexity. So if you want to solve the system of linear equations exactly, again, we're not doing matrix multiplication time and things like that. M square n time, assume that m is smaller than n. So that's the time that you're going to spend. If n is large, this could be too large, so we get rid of n. Essentially, and this is the relevant thing here, every iteration using this in exact solves will take m cubed plus input sparsity time. That's because we use, of course, subspace embedding, the projections that basically can be applied in input sparsity time. And again, a lot of this is sort of vanilla randomized linear algebra, but you make it to play with an iterative procedure here. Okay. Let me wrap up and talk about a couple of open problems, which I think would be interesting from a theoretical and a practical perspective. So we provide structural conditions that have nothing to do with randomized linear algebra, under which, in exactly computing the predictor-corrector steps, which means solving the system of linear equations inexactly, you are able to still return a final solution that is approximately feasible without losing anything in terms of iteration complexity. We provide a way to correct for the error that you incur, and in correcting for this error, you end up with an exactly feasible solution, again, without losing anything in terms of iteration complexity, and you are able to sort of eliminate, to a certain extent, n, the number of variables from the complexity, from the running time complexity. Future work. So all these are for what is called the feasible predictor-corrector, meaning that you start with a feasible solution. If you start with an infeasible solution, there is a recent paper that analyzes predictor-corrector for infeasible predictor-correctors. I mean, it would be a technical thing to actually generalize some of these things to infeasible predictor-corrector IPMs. I don't know if we can get simpler structural conditions. So the results that I showed you are sufficient. I don't know if they are necessary. I don't know if we could do better there. The most interesting thing, I think, from a practical perspective especially, and the theoretical perspective perhaps, would be to understand if the structural conditions could change as we iterate. So right now I have the same structural condition over all iterations. However, it is totally plausible that early on you need more or less accuracy, I guess, and later on you could perhaps work on a GPU. So these days, remember, we have CPUs and GPUs. Maybe some of the operations can be done on a CPU, high accuracy. Some of the operations can be delegated to GPUs that operate on half precision or something. It would be good to understand at which point in the iteration of, let's say, an IPM, you can actually make that switch. This is sometimes called the dynamic preconditioning. Maybe you are going to create a preconditioner that is less accurate or more accurate as the iterations go on. And of course, you could go beyond potentially. IPMs are also useful beyond linear programs. You could look at semi-definite programs. You could look at quadratic programs and see if some of those approaches would be useful as well. Okay, I'm going to wrap it up here and leave a few minutes for questions. Thank you.
Any questions? Yes? Should I bring the mic over?
Thanks. So I was just going to ask about what happens with PCG as you approach termination, because your linear systems can become very poorly conditioned at that point.
So in theory, it doesn't matter. I mean, because I precondition, so it works well, and my precondition is guaranteed to bring the condition number down to a constant. So in theory, it doesn't matter. In practice, I didn't show any experiments here, but in practice, obviously, we observed that as we approach optimality, when the conditioning actually worsens, we did have to get better sketches in the precondition. But we didn't have to run the PCG for more iterations, if that's what you're worrying about.
Like how large are those systems?
We looked at toy systems. I didn't look at the systems that I started with, so I looked at synthetic problems, maybe 100 by 10,000, things like that. I never looked at really large problems.
Yeah, thanks.
I guess. I think this relates to Adrian's question, which is like, you're just looking at error in the solves, but for example, you're assuming you can solve your preconditioned system exactly, which like, given that it's probably itself ill-conditioned, you probably can't do. Like, could you do like an error analysis of the whole thing? Or?
Yeah, so no, we did not try that. Yeah, we thought about this with Chaim. What happens if your precondition is not really computed exactly, right? That's what you're.
I guess what I mean is like you have a preconditioner, which provably gives you a good preconditioner, but therefore it must be ill-conditioned towards the end of that. Like I don't remember what the matrix is. Like ADW must be ill-conditioned eventually.
ADW is ill-conditioned for sure, because AD is ill-conditioned.
Yeah, exactly.
And the problem is that when you invert that, you are in trouble.
Yeah.
Right now, we're not. Yeah, in the analysis, we're not taking.
So you're kind of assuming that's exact.
No,
okay.
Absolutely not. It's the same as blend and pick, LSRN, they all make the same assumption.
Yeah.
Yeah, we black.
But it would be cool to analyze that.
No, you're absolutely right. That would be cool regardless. That would be cool in the context of blended.
Yeah,
right.
Cool.
Absolutely. No, you are correct.
All right, in the interest of time.
Let's thank Petros one more time.